Okay, thank you all for coming, especially after last night's party all over the city. This lecture is going to be a little bit more pictorial and a little bit less technical because everybody's tired. It's also going to be hopefully using components that are a little bit more familiar to people that have more of a topology background than an algorithms background. I know that I'm not going to be able to get through all of my slides, so please don't feel shy about interrupting me with questions. Okay, so I'm going to be talking about untangling and unwinding curves, and the basic structure I'm going to be talking about once again is homotopy. But homotopy for, at least at the beginning, curves in the plane, exactly the process that you're seeing on the screen. The topology of the plane is elementary. Every closed curve in the plane can be continuously transformed into any other closed curve on the plane. So if I start with this complicated picture of an elephant, thanks to, there's a Scottish artist named Mick Burton who likes to draw things with one continuous closed line. I can transform continuously this elephant into a circle. Of course, Mick Burton is not the first to do this, but I couldn't find an earlier example that only went to one curve. So you can also take multiple curves. This is a picture by Paul Klee, the title of which is The Man with the Mouth. The man who likes to talk, seems appropriate. And I can take this collection of curves and simplify them down to the appropriate number, in this case I believe 3, of simple closed curves. But one of the key components of combinatorial topology, and in particular one of the groundworks of combinatorial knot theory, is that this continuous deformation process can be broken down into discrete steps using a finite number of elementary transformations. Now, for knot diagrams, these are typically known as Reidemeister moves, but I want to emphasize that I'm not, there's no casing, there's no sense in which one crossing is over or under another. And so to emphasize this, I'm going to refer to these as homotopy moves. And for some reason, the Reidemeister moves and homotopy moves tend to have really horrible names in the literature. So I'm just going to use this number with arrows notation. A 1 to 0 move removes an empty loop. A 2 to 0 move removes an empty bigon. And a 3 to 3 move flips a triangle. Everyone in the room has seen these a couple of times already this week, and hopefully has seen these in the past. And it's a standard result dating back to Alexander's work in the 1920s and Reidemeister's in parallel via the simplicial approximation theorem that any closed curve in the plane can be homotoped to a point, but that homotopy can be decomposed into a finite number of these moves. But in fact, this proof, if you're willing to accept that homotopies are nice as an axiom, dates back to Steinitz a decade before Alexander. But I'm a computer scientist. I don't like results that just say you can do this in a finite number of things. I want to know how many moves are required. And if you go back to the original proof by Steinitz, which I'll actually show you, in 1916, this implies that a quadratic number of moves are always sufficient to simplify any closed curve with n self-intersections. Now, there have been several follow-up results to this. There's a more detailed explanation of Steinitz's proof in Grunbaum's lectures on polytopes. There have been several follow-up results that either give alternate proofs, alternate algorithms, extensions, generalizations, and so forth. There's lots of work on this. The only lower bound that I was aware of before I started working on this a few years ago is the absolutely trivial one. Each homotopy move reduces the number of vertices by at most 2, and therefore you need to perform at least n over 2 of them. Now, Steinitz wasn't working on the topology of curves. Steinitz was working on the geometry of planar graphs. And this was the theorem that normally carries Steinitz's name, is that a graph is the one skeleton of a convex three-dimensional polytope if and only if the graph is planar and three-connected, meaning you need to delete at least 3 edges before the graph falls apart. Now, the way Steinitz proved this theorem is not by considering the graph directly, but by introducing a structure that we now know as the medial graph. This construction was actually previously used by Tate 40 years earlier in his enumeration of knots, but in the other direction. He went from the medial graph, from the drawing of the knot, to the anti-medial graph, what's sometimes called the Tate graph, for obvious reasons. So given an arbitrary planar graph, the medial graph is defined by putting a vertex in the middle of each edge, and then connecting 2 medial vertices if the corresponding edges are adjacent in cyclic order around a vertex, or equivalently, if they're adjacent in cyclic order around a face. So you get a graph that looks like this. And then if I get rid of the original graph, some structure shows up. This is actually the curve from Gauss's Nachlass. The medial graph is always 4 regular. Every medial vertex has degree 4, because at any edge you can go next or previous at this endpoint, or next and previous at that endpoint. And so the medial graph is the immersion of 1 or more curves into the plane. So then Steinitz observed the following structural lemma about 4 regular planar graphs, but we can specialize it to curves, which is that every 4 regular planar graph, somewhere in there, either it's simple, it's a circle, or it contains an empty loop, which you could immediately get rid of, or it contains a substructure called the bigon. This is a disk bounded by 2 subpaths of the curve, and with some conditions that the ends poke outwards instead of poking inwards. And in particular, you can look for bigons that are inside other bigons, and eventually you get to something called a minimal bigon. This is something a bigon that doesn't have any other bigons inside it. Or as Steinitz called it, you can find ein Spindel, and inside it you can find ein irreducible Spindel. Yes? Oh, no. There could be several of these. The minimal bigons could overlap. There's no uniqueness. It's just there is one. This means that this move reduces the sum of the face depths by exactly 1. Okay, so either there's a 1-0 move, or there's a 2-0 move, or there's a 3-3 move that reduces the sum of the face depths. I'll refer to that as the potential of the curve. And so now we have an even easier algorithm. Do what you can. If there's an empty loop, get rid of it. If there's an empty bigon, get rid of it. Otherwise, there's a positive 3-3 move, reduces the sum of the potential, do it. The potential can't be more than n squared, because a curve that has n vertices, every face has depth at most n, and there are n faces by Euler's formula, And so since every move decreases the potential and the total potential is an integer that starts at n squared, after n squared moves, you've run out of potential to consume. Okay? So these are the classical results. And then recently, my student Shen and I showed that neither of these classical upper or lower bounds is tight. Yes? Oh, I don't know that this analysis is optimal. I'm not trying to make this analysis optimal. I'm just trying to prove an upper bound. Right? In fact, Fayot and Provan themselves conjectured that this analysis is not optimal. Right? Now, I should say, if you choose the positive move to make badly, there are curves which will result in a quadratic number of moves. Okay? The conjecture is that if you choose the deepest positive move, then in fact you only need n to the 1.5 moves. But we don't know how to prove that. Okay? So we were able to prove n to the 1.5 using different methods, and moreover we were able to prove that this bound is tight in the worst case. So the right answer to the question how many moves do you need is n to the 3 halves. Okay, so first I'll describe the new algorithm for the upper bound. I'm going to sort of skate at a high level. I can dive down at any point if you have questions, but I mostly want to get the intuition across. So the upper bound. So what Shen and I did is instead of following Steinitz and shrinking bigons, we look for loops. I think in the time I will flash up the pictures and skip over the details. But we get something that the number of moves you need is MD plus MS. M is the number of vertices, D and S is the depth and the number of strands. So we tighten the strands, then once the strands are simple, we get rid of extra intersections. Getting rid of extra intersections, we do an iterative process where we just basically move strands out of the way and recurse. Now, this running time, MD plus MS, looks a little bit complicated. So in order to make this work and give us a subquadratic number of moves, we need to find tangles that are useful for our analysis. And useful is a term of art. It's a technical term. It means that the number of interior vertices is at least the square of the number of strands, not asymptotically, not omega of s squared, but actually greater than or equal to s squared. The constant matters. But the depth is at most linear in the number of, actually square root of the number of vertices, but intuitively linear in the number of strands. Okay. So if I can find something that has S strands, at least S squared vertices, which means when I reduce, I get rid of a lot of vertices, because I go down from S squared to about S choose 2. But the depth is only square root of the number of vertices, then this bound MD plus MS is just M to the 3 halves. It shrinks down. And that means that I'm spending about square root of n time per vertex that I delete. And then summing that up over all vertices gives me my n to the 3 halves. So the key lemma, useful tangles exist. There's essentially, you can find them by looking at depth contours, finding deepest point and looking at the depth contours that contains it, doing a counting and balancing argument that basically says if the deepest I tangles are all bad, then the perimeter of the tangle must be growing linearly, and eventually you would run out of vertices. Again, I'll let you refer to the paper if you want to see the technical details.
Is the cleanup procedure inside a useful tangle recursive?
No. So the cleanup procedure inside a useful tangle is we get rid of loops using the algorithm that I showed you earlier. Then we get rid of excess intersection between the strands using something that looks like the algorithm that we did for loops, once per strand. So it's just direct. Okay, so we end up with an overall running time of quote unquote, of n to the 3 halves. Yeah.
Do you have something like in this kind of tangle, you have the maximal depth space or something like that?
I'm sorry, could you ask the question again?
In this specific tangle,
yes.
you have some result saying that this is where potentially when you use the other algorithm with the maximal depth always.
Right, so this is, we've tried to do this but have not been able to push the details through. So what we'd like to be able to argue is you go into one of these useful tangles and you take the deepest one. I can always take, you know, the deepest move, and hopefully there's a positive move somewhere inside that deep tangle. Unfortunately, saying it that way, it's a little naive, turns out to be false. So the deepest useful tangle does not necessarily contain a positive move. What we would like is a useful tangle that contains the deepest positive move, and we don't know how to show that that exists. There are generalizations by this way for multiple curves. There's some additional dependence on the number of curves when you do this, and I'll just point to the paper for that. Okay, so this is the upper bound. How do we get the lower bound? Well, for the lower bound, we rely on a curve invariant, not the sum of the depths, but a different curve invariant that was studied by Vladimir Arnold and Francesca Aicardi in the early 90s, which Arnold called the defect. And the defect is originally defined as the unique invariant that is 0 for curves that are simple, and that changes as shown in this picture when you perform a homotopy move, right? And so the big result by Arnold was this is well defined. There is, in fact, a number that satisfies these axioms. In particular, for any homotopy move, the defect either doesn't change at all or it changes by exactly 2, either up or down. And so immediately, given the existence of this invariant, it follows that the number of moves you need to simplify any curve is at least the absolute value of half of the defect. Because if I start with a curve with large defect, each homotopy move decreases or increases the defect by at most 2, and I have to get to 0 in the end. Yeah?
What do those numbers represent?
The numbers inside the faces represent the number of pairs of vertices in the picture that are interlaced in the curve. So this will make a little bit more sense on the next slide. So if you remember, here's the picture of Gauss's curve. If I look, for example, at vertices A and B, those are interlaced. If I walk around the curve, I see A, then I see B, then I see A, then I see B. Right? So here, if there's a bigon where the bigon, if you cut the bigon, it disconnects the curve, then you would see AA and then BB. So there's no interlaced pair. Whereas if it's more mixed, then you'll see A, then B, then A, then B. And that's the difference between whether performing the move doesn't change the defect at all or changes it by 2. And for 3-3 moves, there are 2 pairs of cases depending on which direction you go. So a few years after Arnold introduced this invariant. Polyak came up with an explicit formula for it. So the formula we in the end never actually used, but just to convince you that the invariant is well defined, rather than going through the existence proof, here's the formula. You can verify for yourself that it satisfies the conditions on the previous slide. So it's a sum over all pairs of vertices that are interlaced of the product of the signs, and that -2 there is just a historical artifact from the way that Arnold defined it. Okay. So immediately you see that there's something that is trivially at most quadratic. At most, you're going to be summing over all pairs of vertices, and the thing that you're summing is either 1 or -1. It turns out the defect can't be quadratic. It can only be n to the 3/2, and that actually follows from the fact that we can simplify curves in n to the 3/2 moves. This also turns out to be up to a factor of, I believe, 24, the expected value of the Casson invariant of a random knot derived from this curve. So given a curve, I can randomly flip a fair independent coin for each crossing to decide whether it's over or under, and then I can compute the Casson invariant of that knot. And if I average over all possible over-under assignments, then what I end up with is, I think, like I said, 1/24 of the defect. So we just need curves that have large defect, and it turns out the right curves to study for this are standard projections of standard torus knots, spirograph curves, star polygons, those things studied by Thomas of Bradwardine in the 1300s. So here's the parametric formula for the standard torus knots and a few examples. These look, pretty in spirography. And we were able to generalize results from earlier papers. So 2014, Evan Zohar et al., one of the et als is Joel. And a couple of years earlier, a set of Japanese authors studied these flat torus knots where the number of times you wind around is either 1 greater or 1 smaller than the number of times you oscillate back and forth between the inner and outer radius. And you'll notice that the bound that you get is n to the 3/2. So because there are curves that have defect n to the 3/2, I know that I need at least n to the 3/2 moves to simplify those curves. Interestingly, there are flat torus knots that have only small defect. I don't know if Joel is going to talk about this, but it's an interesting question for people who are interested in random knots, whether this family of Fibonacci flat torus knots are what are called universal, meaning that for any knot type, there is a Fibonacci torus knot such that if you assign the crossings correctly, you get a diagram for that knot. If that's true, then this would give you a family of random knots where the expected Casson invariant is only linear instead of only n to the 3/2. Yeah. That's right. You made some final corrections, which I haven't propagated to my slides. So ask him. Let me skip over now. Okay, I'll go through the couple of open problems here. One is that both Steinitz's algorithm and Theorem and Provon's algorithm have this wonderful feature that the number of vertices never goes up. Whereas our algorithm, at some point, we do have to make the curve more complicated. And we don't know whether that's a requirement in order to break the quadratic upper bound, or if it's just a stupid feature of our algorithm. So are there curves that can be simplified monotonically using n to the can every curve be simplified monotonically using n to the 3/2 moves? Or does monotonicity increase the lower bound to n squared, or is it something in between? And there are a couple of different ways that we tried to do this. One of these is to focus on tangles and say, maybe there's a way to zoom in on a tangle and just simplify the tangle monotonically. And then we could replace our existing tangle algorithm with essentially Fayot and Provon's tangle algorithm. Unfortunately, this is false. There are tangles like this one. There's an infinite family where no move decreases the potential of the tangle. Right, this is what I was referring to earlier. The other possibility is maybe we could try to improve Steinitz's algorithm. Maybe we can find a bigon that always has small area. And then we just shrink the smallest bigon and then recurse. And if the smallest area bigon had only area square root of n, this would immediately give us an n to the 3/2 algorithm. Unfortunately, this turns out to be false as well. And here's the example. This is my favorite planar graph called the Fibonacci cube. So I load up the 6 sides of a cube with a Fibonacci n by Fibonacci n minus 1 rotated lattice. And then I glue these together. So this graph has, every vertex has degree 4. Every face has degree 4 except the 8 corners, which have degree 3. And this particular, it's not actually a curve, it's a multi-curve, but has the feature that every bigon, here's one, uses a constant fraction of the faces. This is a nice feature of Fibonacci numbers. It's a bit of number theory. Here's another bigon. So it looks like a rectangle, but the curve that goes down and to the left actually gets glued to that line that goes up and to the left. So there really are, the only real corners are the ones you actually see in the interior of the cube faces. So we can't just say find the best bigon and reduce it, because at least the first bigon might need a linear number of moves to reduce. Okay. Now,
So why does that kill the conjecture? Like maybe after you use this first one, then...
well, it doesn't necessarily, well, what kills, the conjecture that it kills is there is a bigon with sublinear area, right? It doesn't necessarily kill the conjecture if we shrink the smallest bigon and recurse, that will be subquadratic, because once you shrink one bigon, maybe the rest of the bigons are small. Again, it's hard to think about these things. Now, why did I start looking at this problem? These are the slides that I wasn't going to put in, but after the talk Tuesday afternoon, I felt the need to put them back. The reason I started looking at this problem actually had nothing to do with topology, or so I thought. I was interested in a question about planar graphs. So if you have ever taken an elementary electrical engineering course, or maybe you've seen this as a module in a physics course, where you might be asked to analyze networks of resistors. If you're wondering why I haven't drawn the squiggly lines on these edges, that's because I'm lazy. Okay, so you can imagine an electrical network where it's just a graph where every edge has a resistor on it. And if I inject current at 2 nodes, some voltage differential will happen across those 2 nodes. And effectively, the entire circuit acts like a single resistor. And a standard exercise is to figure out what that single resistor's resistance is. And back in the late 1800s, Kennelly showed that the following sequence of graph operations can be used to simplify circuits and retain information about the resistance. So if I have a loop, I know there's no voltage difference between the 2 ends of that loop because they're the same, so I can just throw it out. If I have a leaf somewhere going off to a node of degree 1, I know there's no current flowing down that edge, so I can just get rid of it. If I have 2 resistors in parallel or 2 resistors in series, I can replace them with a single resistor. And if I have a triangle, I can replace it with a y, and if I have a y, I can replace it with a triangle. And the new resistances of the new 3 resistors are simple rational functions of the resistances that I started with. Lots of other applications of these electrical things. I won't say much more. But it's sort of interesting to observe that these electrical transformations show up in 3 dual pairs. The dual of a series reduction is a parallel reduction. The dual of a loop reduction is a leaf reduction. The dual of a delta to y transformation is a y to delta transformation. So going back to Steinitz, Steinitz's analysis actually shows that any planar graph can be reduced to a single vertex using a finite number of these transformations. And, well, of course, I want to know how many. And again, the way Steinitz approaches this is he defines a medial graph and he builds this thing. And so he thinks about electrical moves, but he thinks about them in the medial graph. You've seen these. This is why I needed to put this slide up. This is, that I had no idea that these, what we call medial electrical moves, had anything to do with the filling area conjecture, but they do. So maybe the stuff that we've been looking at has some other mathematical applications that we're not aware of. So these things look almost like homotopy moves. Okay, great. We were actually able to connect, by close reading of other papers, the number of electrical transformations you need to reduce a planar graph to the number of homotopy moves that you need to simplify a planar curve by looking through this medial lens. And the key tool that we used is something that graph theorists refer to as taking the minor of a graph. So a minor is of a graph is anything you can get to by either deleting edges or contracting edges. Well, what happens, I'm doing everything through a medial lens, so what happens when I look at the medial graph of a graph and medial graph of its minors? Well, we've seen this before. This is exactly smoothing where this way is Gauss and that way is Dane, or vice versa, depending on how you orient the curve. And so by looking at smoothings, which are really just minors, and looking carefully at results in earlier papers, we could show first a kind of monotonicity argument that if you make the graph simpler, the number of electrical moves you need goes down. This is just case analysis. And then a consequence of that is that the minimum number of electrical moves you need to reduce a graph is at least as large as the number of homotopy moves you need to reduce its medial graph. And since we just proved that the number of homotopy moves you need to reduce a curve is at least n to the 3/2, that implies that if I want to electrically reduce this graph, I need at least n to the 3/2 moves because its medial graph is a flat torus knot.
That was a bit quick. The 2 slides back, the connection here. What's so the 2-1 doesn't cause a problem?
So I mean, basically the proof is you run the electrical reduction until you get to a 2-1 move, and then you do a 2-0 move instead. And by the monotonicity lemma, that going from the result of the 2-1 to the result of the 2-0 only helped you. Okay. So if you're ever teaching a circuit analysis course and you want to be mean to your students, use that graph. Okay, so yes. Again, this really follows by close reading of a paper by Noble and Welsh, who were interested. Shen, do you remember why they were looking at this?
So they're studying like 4 different types of graph reduction operations that predicts, basically theorizing the graphs, right? But then they want to understand the power of each of them. They don't really care about the quantitative bound, they just want to see if they have the ability to reduce the graph.
Yeah, so to repeat what he said, what Noble and Welsh were interested in studying is if you have graphs that can be reduced with this family of operations, then can they also be reduced with that family of operations? And basically all we did is, by reading their proof more closely, show that there's an actual quantitative relationship in the case of this pair of moves. Okay. So, topology. What happens when we go to surfaces of higher genus? So exactly the same argument that shows that you can simplify any planar curve using a finite number of homotopy moves shows that you can reduce any curve on any surface to minimal position, to as few intersections as possible using a finite number of homotopy moves. What about lower bounds? So we were actually able, this is joint work with Saul and other people who aren't, and Arno and other people who aren't here. And Eric? Eric, are you here still? Okay. This is joint work with everybody in this room. Except me, I'm not here. We first showed that we can improve the end of the 3/2 lower bound to n squared on any non-trivial surface, even when the curve happens to be contractible. And then results by Joel and Peter Scott actually imply that this n squared bound is tight. There's an n squared upper bound for contractible curves because the result in Haas and Scott implies that for any contractible curve on any orientable surface, there is either a loop or a bigon, exactly the same way, the same conditions as Steinitz, which means you can just apply Steinitz's algorithm. Okay. And to think about how we built this, this curve, it suffices to consider the case where the surface is just an annulus, or really just a punctured plane. There's a planar curve, and there's one point called the origin, which you're not allowed to move the curve over. Now, we first tried to do this with defect, and we were able to show that there are curves on the torus with quadratic defect, but they're not contractible, so that we weren't happy enough with that. So here's the bad curve, or one example of the bad curve. That x in the middle of the plane is the puncture. Obviously, this is one example of an infinite family of curves. You've got the inner tracks of the record, which wind around clockwise, and the outer tracks of the record, which wind around counterclockwise. The inner tracks have this family of interchanges in the middle here. Basically, one interchange between at each column. The outer tracks, you get 2 interchanges at each column. And for those of you who don't remember, records are things that used to play music before. Yeah. Okay, so how do we show that this curve is bad? Well, we go back to our old friend winding number. Okay, remember, before we were proving upper bounds by looking at depth, the kind of unsigned winding number. And to prove the lower bound, we were looking at defects that involved signs and so on. There's another characterization, another formula for defect that involves winding numbers again. So it's fairly natural to look back at this. Yes, this is the same Mick Burton who drew the elephant. So remember, there's this Alexander numbering. The outer face of an oriented curve has Alexander number 0. Every pair of adjacent faces, the winding numbers differ by 1, with the left side being 1 more than the right. Now I can extend the notion of winding number to the winding number of a curve around one of its points by taking the average of the winding numbers in the nearby faces. So in particular, at a vertex, I get an integer winding number by averaging the winding numbers in the 4 faces that are incident to it. And these are always going to be in the pattern W, W, W plus 1, W minus 1. Okay? So I can define the winding number of any vertex of the curve. And then think about what happens to these winding numbers when you perform a homotopy move. Well, any vertex that's not involved in the homotopy move, its winding number is not going to change. If the homotopy move gets rid of vertices, obviously their winding numbers aren't defined after they don't exist. And with a 3-3 move, you can think of a 3-3 move as moving one strand of the curve over one vertex. And so the winding number at that vertex either goes up or down by exactly 1. And this happens for all 3 vertices. So winding number changes at those 3 vertices by 1, and that's the only way that homotopy moves can change winding numbers. Now I'm going to define a second number for every vertex, and as far as I know, this is new. So let me do the Gauss smoothing at a vertex, splitting the curve into 2 subcurves. And I'll define the type of a vertex as the winding number of the subcurve on the left around the puncture. Right, so instead of the curve, how does it wind around the vertex, I'm going to take a subcurve and how does it wind around the puncture. Okay? And I'll say that 2 vertices have complementary types if those winding numbers are complementary. So the winding number of the entire curve, I'm assuming it's contractible, so the winding number is 0. So these 2 subcurves, because winding numbers are additive, will have complementary winding numbers. One will have winding number 5, the other minus 5 for some value of 5. 2 vertices are complementary if when I smooth them, the subcurves on the left have opposite types. Okay, now how do types change when I do homotopy moves? Well, they don't. Types never change. But we can say something further. When you delete a loop with a 1 to 0 move, by definition, that loop that you deleted is contractible. And so the winding number of the 2 curves you get when you smooth at that loop, those are both wind 0 times around the puncture. So the only way you can get rid of a vertex is if that vertex, with a 1-0 move, is if that vertex has type 0. On the other hand, a bit of case analysis shows that when you do a 2 to 0 move, those 2 vertices that you delete have complementary types. So if you have a vertex of type 3 and a vertex of type -6, those vertices will retain their types as you move them around by homotopy, but they will never meet and be canceled by a 2 to 0 move because they're the wrong species. So I can go back to my old curve, and here I've identified the types and the winding numbers of all the vertices. So the blue numbers along the bottom show you the winding numbers of all the vertices directly above them. The red numbers attached to the vertices show you the types of those vertices. And this vertex over here on the left that has type 2 must eventually be canceled by a vertex over here on the right that has type -2. Right? So any homotopy that contracts this curve defines a matching between vertices of complementary types. Now, this is true even if I create new vertices. When I create new vertices with a 0 to 2 move, those vertices have complementary types, and one of them might cancel out some older vertex. Basically, you can just trace through backwards and forwards in time from a vertex of type 2, maybe to a vertex of type -2. So I get this lovely little matching. Here's 2 edges of the matching. And for this particular curve, a constant fraction of the types, those 2 vertices differ in winding number by by something proportional to n. So I have n pairs, each of which have winding distance n, and because each move only changes 3 winding numbers, I need to perform a quadratic number of moves in order to bring the complementary vertices together to cancel out. I would love to hear that this winding distance invariant was studied by Roger Bacon in the 1500s. I would love to know if this winding invariant has other applications or has been looked at in any context before. But as far as I can tell, this seems to be new. Okay, so quadratic, even if the curve's contractible. What about the upper bound? Well, so we were actually able to prove with, all of us in this room were actually able to prove a polynomial upper bound for higher genus curves. And basically, most of the hard work was done in these 2 papers. In particular, this paper here on the left by Joel Haas and Peter Scott has a really very, very subtle key lemma in it, which I'll show you, but not the proof, because you don't want to see the proof in a lecture like this. It's really quite a technical tour de force. So thank you, Joel, for doing the hard work so we don't have to. And then a lot of insight, although I don't think we ended up actually using many of the tools from de Graaf and Schrijver, but some of the later results that showed up in Xian's thesis, which will appear any day now, do rely heavily on results from this paper and other papers by de Graaf and Schrijver. So unfortunately, so just to establish some vocabulary, I'll say that a curve is tight if it's in minimal position, because tight has fewer syllables than minimal position, and loose otherwise, because loose has fewer syllables than not in minimal position. And you'll notice by looking at this curve already, we run into a problem with Steinitz's algorithm. So this is a pair of closed curves in a pair of pants that are homotopic, and clearly homotopic. But you'll notice that there are no loops or empty bigons in this curve at all. There's a loop, there are 3 loops, but they all contain punctures, so I'm not allowed to move them. Nevertheless, it's possible using arguments based on curve shortening flow or more combinatorial arguments later that you can tighten any curve using a finite number of homotopy moves. Upper bounds that were previously known, except for a few special cases like contractible curves or curves on the torus, nothing non-trivial was known. The previous upper bound that we had is this monster that basically follows from the fact that this is an upper bound on the number of 4 regular graphs that you can put on a surface of genus G that have n vertices. Okay. So we were able to bring this down to about n to the 4th, actually slightly better than n to the 4th. And as I said, bigons and loops don't necessarily exist, and so we have to work a little bit harder. So what Haas and Scott observed is there's something like a loop or like a monogon or like a bigon, which they call a singular monogon, a singular bigon. So a singular monogon is just a contractible loop in the curve. And close reading of Peter and Joel's paper shows that you can actually consider what we now call a basic singular bigon, which is this red loop. If I lift it up to the universal cover, it's actually simple. It's actually embedded. Okay. Similarly, a singular bigon is a pair of homotopic subpaths that come from disjoint arcs on the circle. And a singular bigon is basic if, when you lift to the universal cover, it really looks like a bigon. Okay. And so the really important key result from Haas and Scott is that even when you don't have embedded loops or embedded bigons. As long as the surface is orientable, we can always find a basic singular monogon or a basic singular bigon. And so this gives us a head start. Maybe what we can do instead of looking for embedded bigons or embedded loops is we can look for these singular things and try to follow Steinitz or try to follow our loop reduction algorithm to empty out these singular bigons, and somehow the details will work out with the universal cover and the projection. No. So even though you have these singular things, the singular version of Steinitz's algorithm still doesn't work. So I noticed that because this graph is drawn on this curve is drawn on the torus, there are real bigons in the picture. I know that I could have reduced that real bigon instead of this one, but then the universal cover drawing would have been uglier. So here's a singular bigon. Up in the universal cover, I see that it has a triangle in the corner. So let me try to get rid of that triangle in the corner. And what happens is that even though I'm removing a triangle from the right side of the bigon, I'm inserting a new triangle into the left side of the bigon. So when I naively try to make the bigon simpler, I end up just moving the complexity around because of different translates of the same vertex play different roles in different parts of the lifted bigon. And so we have to be much more careful. So first, we decompose the surface into a canonical structure, essentially to give us ways of isolating parts of the universal cover that we can treat independently. The structure that turned out to be useful for us was a reduced dual cut graph of a triangulation of the curve, which when you lift to the universal cover gives you a regular tiling of 6 gigons meeting 3 at a vertex. And you can already guess that we're going to be applying Dane's isoparametric stuff upstairs in this universal cover. Now the high-level strategy then is we're going to look for a basic singular monogon or bigon. If it's a monogon, we'll do a 0-1 move to turn it into a bigon. Now we only have to think about bigons. This picture is the lift of the singular bigon up to the universal cover. It's carved into a bunch of pieces by the tiling. Those red lines are the edges of the tiling, or a cartoon of the edges of the tiling. The intersection can be all kinds of ugly. Just all we know is any interior vertices have degree 3. So instead of just trying to empty the bigon, the way we're going to do this is we'll move the ceiling of the lifted bigon down to the floor. We'll unzip the floor and the ceiling, and then we'll move what used to be the floor of the bigon back up to the ceiling. Notice what happens is that the number of vertices before decreases by 2 to the number of vertices after. The only difference between the two, the before picture on the top left and the after picture on the bottom left, is that I've resolved these two vertices. So even though locally I may not be reducing the number of vertices, at each stage I've resolved one bigon, thereby reducing the number of vertices by 2. So as long as I can use, so I know after a linear number of these stages I will have gotten rid of all of the vertices. Okay. Now, this tiling inside the bigon isn't that complicated. The way we construct the dual reduced cut graph, we know that the curve intersects each arc of the tiling at most once, and so the total perimeter of this bigon is only linear. The discrete Gauss-Bonnet theorem implies that the area of this bigon is only linear. And so in some sense, we can bound the amount of stuff that's going on inside this bigon. Now, actually moving the top of the curve down to the bottom, we decompose that by looking at it a couple of levels of detail. At the coarsest level of detail, we pretend to be Dane. we use moves in the tiling or in the fragments of the tiling that it resembled the original 1911 algorithm by Max Dane for proving that loops are contractible or not. So we have moves in the tiling that either we can move the curve that we're trying to translate across a face, or we can push it across an arc of the tiling. And then later, this is going to double things up along the edges of the arc, the arcs of the tiling. Later, in order to continue moving it all the way down, we'll need to do the sort of duals of these. We'll need to remove spikes, and we'll need to move the moving frontier across a node of the tiling. And we just do this carefully because the total complexity of the graph, of the red graph inside that bigon is linear. I need a linear number of graph moves to move the ceiling down to the floor. Now, the reason why we're introducing this tiling and we're doing these graph moves is that while I'm doing something inside one tile, there's other stuff happening in parallel in other translates of that tile, but only in the other translates. Within one tile, that tile will project down injectively onto the surface. But to do this really carefully, we actually need to define some neighborhoods of an open cover of the surface where we can do the moves inside these open balls. In particular, we do our face moves inside an inset open neighborhood of the face. We do our node moves inside open neighborhoods of the nodes, and we do our arc and spike moves inside open sets that avoid the endpoints but otherwise cover the edges. And some analysis. This is where more factors of n creep in. Yeah, Matthias.
May I show my ignorance?
I'm sorry.
So do you work in a lift, or do you simply look at the entire inverse image on the...
Okay, so this is a good question. Are we working in the lift or are we working down on the surface? Every move we perform on the surface. But in order to do the analysis, we have to think about what's happening upstairs. So when I move this black curve, say from that top, I push it down through that face. We know that other translates of that black curve will also move, but that movement will not happen inside that face. So the way we do the analysis is we say, when we're about to do a move inside this part of this tile, let me just analyze how much is happening inside this tile, because that will project down injectively onto the surface, and that will tell me how much work I'm doing down on the surface.
So basically, why is it guaranteed that this tile doesn't overlap with itself?
Because of the way we constructed the tile. The tile is the lift of that disk, or rather the interior of that disk, that you get by taking a cut graph and cutting the surface open.
Okay.
Right? So the overlaps can only happen at the boundaries, but because we inset, we know there's no overlap. Okay. So the punchline is that by being very careful, we can show that every face move in this coarse homotopy can actually be decomposed into a linear number of Reidemeister-style homotopy moves, essentially by mirroring the algorithm I showed you in the plane. And the other moves, because those bubbles around the edges and faces, this is where things accumulate, I actually need to do a quadratic number of homotopy moves in order to execute a single graph move. In the end, what we get is the following analysis. We can always find a basic singular bigon, and so if we get rid of it, we need to do that n times. So there are n singular bigons that need to be resolved. For each singular bigon, we can resolve it at a very coarse level, just looking at this tiling, using a linear number of graph homotopy moves. And then looking more finely within these node, arc, and face bubbles, we can decompose each of those graph moves into a quadratic number of homotopy moves. And so altogether, we end up with an upper bound of n to the fourth. Now, in a few cases, we can actually improve this. So the end of the fourth bound, some later ongoing work by Arnaud and Chen, they were able to reduce the n to the fourth down to something like n cubed, at least when the genus is fixed, by choosing the coarse homotopy more carefully. So we just picked the coarse homotopy that worked. But if you vaguely recall from Aaron's lecture, there's this notion of homotopy height. I want a homotopy that keeps the length of the curve as short as possible. If you apply the log n approximation algorithm for homotopy height by Sariel Amir and others, we can actually reduce the number of graph moves down from n to g log squared n. And then the rest of the analysis is the same. Things get a little bit easier when the surface has boundary. So again, we can get down for constant Euler characteristic, we can get down to n cubed moves. In this case, instead of using a tiling where you have got these interior vertices, you use a bunch of arcs, boundary to boundary paths, to cut the surface into a disk. And then in the universal cover, these things glue together like a tree, and trees are nice. And so we can actually get rid of a factor of n in the analysis. But there's still a bunch of open problems left. We don't know how to do anything with non-orientable surfaces. And the reason is that Joel and Peter's lemma about basic singular bigons is false when the surface is non-orientable. There may be no singular bigons or singular monogons for a curve drawn on a non-orientable surface. And so we don't know how to start the process of deriving an algorithm. You still can do something when you have a projective plane or a Mobius band. Those things we can analyze separately, but we only get a quadratic upper bound. These things are very, very close to being planar, so maybe that quadratic bound for the projective plane, Mobius band we can't improve because a Mobius band contains an annulus, but the projective plane doesn't contain an annulus, and so we don't know whether the n squared bound should be really n to the 3 halves or not. But for more general non-orientable surfaces, the only upper bounds we know are the more or less trivial n to the order g2 to the order n. And so really nothing is known here. None of our results extend so far to multiple curves. We really are analyzing a single curve. This is probably the most accessible of these open problems, but there are some subtle details that happen with multiple curves because things can be nested and you have to push them out of the way. So there's definitely going to be some kind of dependence on the number of constituent curves, but again, at this point, the most I can claim is finite or exponential. And then finally, again, just like the planar setting, we sometimes have to make the curve more complicated before we make it simpler again. The finiteness results by Haas and Scott and the curve shortening flow and all these things, those all imply that it's possible with a finite number of moves to simplify always moving down. We don't know whether we can do that with a polynomial number of moves. I understand that Arnaud and Cien are getting close. There's some progress, but I'll just, without giving away any details, I'll just say, coming soon, sometime before the next Avengers movie, we'll get another paper. And so here's the state of the art for the number of moves, upper and lower bounds. We have tight results in the sphere of the plane. We have tight results in the annulus or any sphere with holes. We have tight results for the torus and in orientable surfaces when the curve can be simplified to have no intersections. And we don't have tight results in all of the other cases. Okay. And with that, I want to thank you for your attention all week long. I know this has been a long and exhausting week. I appreciate the fact that you've been coming and paying attention and asking lots of questions. I'm happy to take more, but this is the end of my talk. Thanks. Yes, and then somehow I have to make the moves in both parts of the double cover simultaneously. And I get this weird interference thing that happens again.
All right. More questions? Thank you again.
Okay, thank you.